Well, we'll assume that we didn't miss anything there. Or if I did talk about SSEs, Ed is now an engineer, got a degree from App State. So it's not a permanent condition. All right, so what is the momentum of the 6 kilogram mass?
6 kilograms meters per second.
No. Although I was expecting someone to say it.
Oh, negative.
Because whether the person was thinking it or not, whoever said 12 first, at that point established the convention. We're dealing with vectors, there is a positive and negative direction. If the person had said negative 12, that would have been fine, that would just define positive in the other direction. But this sets our convention that to the right is positive. And so P6 initial is 6 kilogram meters per second. Now personally, I hate writing kilogram meters per second over and over again. And some students just stick with Newton seconds because that's fine. And some students, which I will allow, can make up their own unit. The rules are, you have to write it at the top of the page somewhere so that I know you're defining it as such. Since this is not internationally accepted, don't just use what I'm using without defining it, or make up your own. Just because you do it on one paper does not make it true for everything you ever do for the rest of your life. Do not pick a letter that's already being used. If your name is Nick and you want to honor yourself with a capital N, no. N is already being used for Newton. Capital D is not used for anything, so I sometimes will define that as a kilogram meter per second, and then I'll just use D. D for Descartes, as in Rene Descartes. The I think therefore I am guy. So this would be 6 Descartes, and this would be 12 Descartes. Oh, sorry, negative 6 Descartes. Lost the negative sign there. All right, so now, what is the total momentum before the collision?
6 Descartes. Oh,
How'd you get that?
well, I just put them together.
Through what magic?
I just added negative 6 to 12.
Yeah, and that's all you do. So P initial, 6 Descartes, and this comes from 12 plus negative 6. After they collide, what is their final momentum?
What we just said?
Why?
Oh, the final.
Yeah, final.
6 Descartes.
Yeah.
I was gonna say, it was tricking me.
No, it's a lot easier than you think. I've asked this on a test before and just shocked at, no tears yet, but close to tears of the number of students who did not recognize that momentum was supposed to be conserved and the total before equals the total afterwards.
In a closed system.
Say it again?
In a closed system.
Yes, in a closed system.
So,
Olivia.
on a test, are we just supposed to assume it's a closed system unless otherwise told, since we're only given like those numbers and like,
Yeah.
we're just supposed to assume?
And I will tell you on that last test, there will be a 2 objects colliding into each other problem
Okay,
And it's closed.
in a closed system.
so I'll just assume it's a closed system, unless otherwise specified.
Unless
Or just
otherwise
right.
stated or heavily implied.
Okay.
How would you know it's an open system?
If an object's accelerating and I haven't really told you what's causing it.
Okay.
Yeah.
So that's another force or?
It would be other if I don't tell you. And other are the forces that I don't tell you about, but you know have to be there, or forces that you really don't care what's causing it. All right. In a collision problem, you can Yes, in a collision problem, you can assume closed system unless I explicitly state otherwise. All right, so I know the final momentum, and that's got to be equal to the final mass times the final velocity. What is the final mass?
Of the masses together while they're stuck together?
Yeah, well, I mean, they stick together, so what's the final mass?
9
Yeah.
kilograms.
So 6 Descartes is equal to 9 kilograms times my final velocity. And so my final velocity, 2/3 meters per second. It is positive, which tells me that when they collide, they're gonna move off in the positive direction. Just a couple of final notes here. If they stick together, this is known as a perfectly inelastic collision. And you'll definitely see this in one of the videos. Some textbooks will call this an inelastic collision when they stick together. Other textbooks will call it perfectly inelastic. It's in the video about the naming convention is, it'd be nice if they standardized it. So just to add to just the lovely aspect of it, I introduced a third naming system. If kinetic energy is conserved, so if the total kinetic energy does not change, this is a perfectly elastic collision. And I will tell you right now, on that last test, I'll have two objects coming towards each other. I will do a perfectly inelastic collision and a perfectly elastic collision. Just let you know ahead of time. Not for the next test, but the last test. And if it's in between, there's a change in kinetic energy, but they don't stick together, that's what I call an imperfect collision. And this is where the mess comes in the naming convention, because some sources will call this situation an elastic collision, and some will call it an inelastic collision. And because people can look at different sources, and apparently I don't have mental capacity for remembering which book does which convention, that's why I came up with my own. So anyway, on that note, as a reminder, and hopefully I'll send out an announcement. If I don't, please, somebody send me an email reminding me to. You're allowed one side of an 8.5 by 11 piece of paper to write whatever you want on it for the test on Thursday. And if you wish to write a manifesto on that 8.5 by 11 piece of paper, that's fine too.